Okay, so welcome back to this next video in which we are discussing the class equation. Okay, so we've now seen how we can view conjugation of the elements of a group by another element of the group as defining this group action of the group capital G on itself. Okay, in this next video what I want to discuss is the concept of a conjugacy class, okay, and the concept of how the conjugacy classes of a group can be used to partition up the group. Okay, and this really comes from considering the orbits of this group action that we've just defined using conjugation. Okay, right, so let me begin discussion of this by drawing a picture. Okay, so we're going to have our group capital G here, okay, and of course our group is actually the set on which the group action is actually acting in the case of this group action of the group on itself. Okay, and we know from our abstract study of group actions that whenever you have a group action by a group capital G on a set capital A, you can use that group action to partition up the set capital A into the orbits of the group action. Okay, what we're now going to do is we're going to partition up the group capital G into the orbits of the group action, okay, which is this group action involving conjugation of the elements of the group by elements of the group. Okay, right, and these orbits are going to be the conjugacy classes of elements of the group. Okay, right, so first I'll just remind you of the definition of an orbit. Then what I'd like to talk about is some special orbits, okay, and then what I'd like to show you is how the conjugacy classes, which are these orbits in the case of this specific group action, are actually going to partition up the group. Okay, now we go through this argument more generally in the video on the orbit stabilizer theorem, okay, but I'd like to repeat it here for the special case of conjugacy classes, okay, for completeness. Right, so firstly let me go through the definition of an orbit and then we'll use that to define what a conjugacy class is. Okay, so for an arbitrary group action then, the orbit of an element little a from the set on which the group is acting, so in this case little a is going to be an element of our group capital G, so I'll add it into our picture here. So let's say we've got little a here, okay, here we go, and I'll just highlight little a up in orange as well. The orbit of this element little a, by definition it's going to be the set of all elements from the set, which in this case is the group, which little a can be moved onto by elements of the group acting on it. So it's going to be all things of the form G dot little a, where G is an element of the group capital G. Okay, so what you're going to do is you're going to go through every element of the group capital G, you're going to act all of those elements of the group on little a, okay, and you're going to see where can little a be sent basically. You're going to list in this set all of the places that the elements of the group G can send little a, and that set, which is a subset of the set on which the group is acting, which in this case of course is the group, okay, is what is meant by the orbit of the element little a. Okay, right, so now let's fill in place of our arbitrary group action here, what our group action actually is in this case. So let's replace G dot little a here with what it's actually going to be equal to in this case. So in this case what it means is little g conjugating the element little a. So what we're actually going to do is for an arbitrary element little a, we're going to go through all other elements of the group. So we're going to go through absolutely all the elements of the group. We're going to conjugate little a by all of those elements of the group. Okay, we're going to get a whole bunch of answers which will again be elements in the group, and we're going to stick all of those answers into a set, and that is what is meant by the orbit of an element little a under this group action. Okay, now we're going to drop the nomenclature of orbit now, and we're going to call these the conjugacy classes. Okay, so this is actually the definition of the conjugacy class of the element little a. So the conjugacy class of this element little a is just the orbit of little a under this group action of the group on itself by conjugation, basically. Okay, so this is the definition of the conjugacy class of an element of the group. So if you've got little a, which is an element of the group, you conjugate little a by all the other elements of the group, collect all of the answers together in this set. That is what is meant by the conjugacy class of an element little a. So to mark it on here, it's a subset of the group capital G. Okay, it could actually end up being the entire group. It's not necessarily going to equal the entire group though. Okay, so it's more generally a subset of the group capital G. Okay, right. So the first thing that I want to do before we go on to the fact that conjugacy classes can be used to partition up the entire group, which of course follows from the fact that they are the orbits of a group action, and we know that the orbits of a group action can be used to partition up the set on which the group is acting. Okay. Before we do that, I want to point out some very special conjugacy classes. Okay, so the special conjugacy classes that I'm going to point out relate to the elements, little a, which are in the centre of the group. Okay, so what is the conjugacy class of an element of the centre of the group going to be? Well, before we can answer that, I'll just remind you of the definition of the centre of the group. So Z of G is called the centre of the group, and there is a video in my playlist on group theory about the centre of a group. Okay, and the definition of the centre of the group is that it's a subset of the elements of the group capital G, and it's in particular the elements of the group capital G which satisfy certain conditions. So it's all the elements of the group capital G which satisfy this special condition, which is that G composed with little s is equal to S composed with little g for absolutely all little s is an element of the group capital G. So basically, the condition to be an element of the centre of a group is that you must commute with absolutely all the other elements of the group. So no matter what little s is from the group, it must be the case that little g composed with little s is equal to little s composed with little g. Okay, so to be in the centre, you have to commute with all other elements of the group. Okay, so let's now think about what happens if we take an element, little a, from the centre of the group and construct the conjugacy class of this element, little a. Okay, well my claim is that if little a is in the centre of the group, then the conjugacy class of little a is very simple. It's the set that just contains the element little a. So it's a set with only one thing in, and that thing is the element little a. Okay, and indeed I should have stressed when we firstly defined conjugacy classes of an element little a, that the element little a will always be in its own conjugacy class, and the reason is that one of the elements of the group that you'll go over here will be the identity element, and the identity element conjugates any element of the group to give back that element of the group. So the first thing to say about conjugacy classes of elements of the group is that the element itself will always be an element of its own conjugacy class. So little a is always an element of the conjugacy class of little a. Okay, but my claim is that if little a is in the centre of the group, then that is the only element in the conjugacy class of little a. There's no more in there. Okay, so why is this going to be the case? Well, let's use then the condition that little a must have obeyed if it was in the conjugacy class of, if it was in the centre of the group. Okay, so if little a was in the centre of the group, what that meant is that little a composed with little s was equal to little s composed with little a for all little s is an element of the group. Okay, so just applying this very definition here. Okay, and what does this mean? Well, we can rearrange this equation very nicely. So what I'm going to do is I'm going to compose each of the sides of this equation on the right with little s inverse. Now when I do that, on this left hand side, when I compose with little s inverse, and I'll try and squash it in here because we're running out of space, when I put little s inverse in there, okay, what will happen? The little s will combine with the little s inverse to give me the identity. So on the left hand side of the equation, I'll just get little a, okay, and on the right hand side, I'll get s inverse, okay. So, in fact, this condition here, the original condition that we had, that the element must commute with all other elements of the group, this can be rewritten like so. which is the condition that if I conjugate the element little a by any element of the group, so whatever little s you pick from the group, if you use that element little s to conjugate the element little a, you must get little a back again. So in fact, the elements of the centre of the group, equivalent to this definition here, they are the elements of the group which, if you conjugate them by any other element of the group, give you back themselves, basically. Okay, so conjugation has absolutely no effect on the elements of the centre of the group. So if you've got an element of the centre of the group, you can conjugate it by any element of the group you like, any little s that you like, and it will have no effect. You'll just get little a back again. Okay, so that then tells us that the conjugacy class of this element little a must actually be this set that just contains the element little a, because if I want to construct the conjugacy class of little a, what I'm going to do is I'm going to go through all the elements of the group and use them to conjugate this element little a. But I've just said that conjugation has no effect if little a is in the centre of the group. So the only answer I'm going to get again and again and again will be little a here. Okay, so the only element then that will end up in the conjugacy class of little a will in fact be the element little a itself. So that is why the conjugacy class of an element little a, which is in the centre of the group, is just this set that contains the single element little a. Okay, right, so those are some special conjugacy classes then, the conjugacy classes that contain only one element. If an element is not in the centre of the group, then it must be the case that you cannot conjugate it by every single element of the group and just get a back again. Okay, so if a is not in the centre of the group, then the conjugacy class of little a must contain more than just little a. Otherwise, if it did just contain little a, then what would that actually mean? That would mean that I could conjugate little a by any other element of the group and just get little a back again, but I've shown that that is the equivalent definition to this. So if it was true that the conjugacy class of little a just contains little a, then it would be true that little a was in the centre of the group. So this works both ways. If little a is in the centre of the group, then the conjugacy class of little a is just this set containing little a. If the conjugacy class of little a is this set just containing little a, then it implies that little a is an element of the centre of the group. Okay, right, so we'll come back to that when we come on to the class equation, but for now I'm going to step away from this and we're going to talk about the fact that the conjugacy classes are actually going to partition up our group capital G. Okay, so going over the page then, I'll draw a picture here which we'll use to discuss this fact. So once again, here is our group capital G, and I think I'll go back to colouring it in turquoise because that was the colour that I was originally denoting the group that was just the set that was being acted upon by the group action. Okay, so we've got our group here, okay, and what I now want to discuss is that actually you can use the conjugacy classes of elements of the group to partition up the group into subsets, okay, and the reason of course is that the conjugacy classes are equivalent to the orbits of this group action, and we've seen in the video on the orbit stabilizer theorem that you can always use the orbits of a group action to partition up the set capital A on which the group action is working. Okay, so that argument applies just as well here. However, what I want to do is go over the argument again so that this video stands on its own, because it's not the simplest argument in the world, okay, and it's a really important point. So I want to go over the argument as to why the conjugacy classes successfully partition up the group capital G here now. Okay, and I'll do it specifically for conjugacy classes rather than for a general orbit of a group action. Okay, right, so let's firstly start off with the conjugacy class that contains an element little a. Okay, so here we have this subset, which is the conjugacy class that contains the element little a, and we've seen the definition of the conjugacy class of an element little a, but I'll just rewrite it out here because it's going to be incredibly important. Okay, so the conjugacy class of an element little a within our group is the subset of the group which contains all things of the form GA, G inverse, where you let little g vary over all elements of the group. So you go through every element of the group and you use every element of the group to conjugate the element little a. All of the answers you get, you stick those into this set, and that is what is meant by the conjugacy class of the element little a. Now, we've seen that if little a is an element of the centre of the group, this is just going to be a set containing one thing. If it's not an element of the centre of a group, then it will contain more than one thing. Okay? What I now want to show you is a really important point, which is the point that even if it contains more than one thing, if you pick any other element of this conjugacy class of the element little a and generate its conjugacy class, you will end up with the exact same set. So this is my next point, that if we have another element in the conjugacy class of this element little a, okay, and I know this won't be true if little a is in the centre of the group, but if it's in the centre of the group, then it's always true anyway that any element that you can pick from that conjugacy class will generate the same conjugacy class, because the only element that you can pick is little a. I'll come back to that point later on. But let's assume that we've got a conjugacy class that contains more than just one element. Okay, so if you pick any other element of the conjugacy class of little a, okay, and generate its conjugacy class, it's going to be the exact same set. So let's take some arbitrary other elements. Now, how can we write an arbitrary other element of the conjugacy class of little a? Well, the way that we can write it is GA G inverse, where G is some element of the group. So this other element of the conjugacy class of little a is of this form, basically. Okay, it is the conjugate of the element little a under this element little g, where little g is some element of the group capital G. Okay, so here I've got some arbitrary other element of the conjugacy class of little a. So I'll write this out. This is an element of the conjugacy class of little a. And basically what I now want to show you, and this is going to be so important for why these conjugacy classes can partition up the group in a well-defined way, is that if I now consider what the conjugacy class of this element, GA G inverse is, that it is actually equal to the same as the conjugacy class of little a. So basically, in fact, for any conjugacy class of the group capital G, you can take any element of that conjugacy class and generate its conjugacy class, and it will be the same, basically. So really it didn't matter that we picked little a to generate this conjugacy class. You could have used any of the elements that are in that same conjugacy class as little a. Okay, so this is what I want to prove then. Okay, so how am I going to show this? Well, quite simply, I'm going to use the definition for the conjugacy class of this element, little g, little a, little g inverse here. Okay, so the definition of this is that I need to conjugate this element of the group, little g, a, g inverse, by absolutely every single element of the group and collect all of the answers into the set. Okay, so I need some new notation because I've now used little g, so I can't let little g be the thing that varies over all elements of the group. So instead I'll take little g bar here. Okay, so little g bar, little g, a, g inverse here, and then on the other side I'll need g bar inverse. And this time it's little g bar that is varying over all elements of the group. So I just want to stress one thing here, that little g is now fixed. It's the fixed element that creates this element of the conjugacy class of this element little a. Okay, little g bar is now the thing that is allowed to vary over all elements of the group. So this quite simply says, take this element GA, G inverse here, and conjugate it by every other element of the group. And that's just exactly the definition of the conjugacy class of this element GA, G inverse. Okay, right. Now what I'm going to do is I'm just going to change where I put the brackets. Now I'm perfectly allowed to do that because of course I've just got 5 things composed together in my group composition table, and my group composition table obeys associativity, so it doesn't matter where I put the brackets. So I'm just going to rewrite this in the form now as G bar G, okay, and then I'm going to have A, and then I'll have G inverse G bar inverse, but I'm going to rewrite G inverse G bar inverse as well. I'm going to rewrite that as G bar G inverse, because of course this is equal to G bar G inverse. These two elements composed together, they're inverse. Okay, so I've just taken G inverse G bar inverse and rewritten it as G bar G inverse, the inverse of G bar composed with G. So that means that I can rewrite all of the elements of this set in the form G bar G A G bar G inverse. Okay, so basically what I'm doing is I'm conjugating the element little a by the element G bar G. Okay, now why does that mean that this set is actually going to end up being the same as the conjugacy class of the element little a? Well, let me just write it out in full here. So this set is exactly the same as G bar G A G bar G inverse, and I'm letting G bar vary over all elements of the group. Okay, well hopefully you can probably understand this by now, because this is an argument that we've seen many times before in this playlist on group theory, and this is the argument that if I let G bar vary over all elements of the group, then this element here, G bar G, will end up varying over all elements of the group, because effectively what I'm doing is, if we think about the group composition table, okay, so here's the group composition table, I'm looking effectively at the column dedicated to this fixed element little g. Okay, I am going through every single element of the group here, okay, every element of the group G bar, okay, so this is the portion corresponding to G bar here. Okay, I'm going through every element of the group G bar, and I'm asking what do I get once I've multiplied it by this element little g. So once I've constructed G bar G, and I'm just effectively constructing this entire column here. And we know that the rows and columns of a group composition table contain every element of the group once and only once. So basically, if you let G bar vary over all elements of the group, you will get G bar G varying over all elements of the group, because that's just this set which is the column corresponding to little g, and that has to contain all elements of the group. So effectively what you can do is replace this with some new variable which we can call G double bar, and then we'll have G double bar inverse over here, and we can say that G double bar is going to vary over all elements of the group. Okay, so that now proves then that this set, which is the conjugacy class of this element GAG inverse, is actually the same as the set which lets G double bar vary over all elements of the group and conjugates this element little a by all elements of the group, and of course that's just the definition of the conjugacy class of this element little a. Okay, so that then is how I can prove that the conjugacy class of any other element of this conjugacy class of A is in fact the same set. It's the same as the conjugacy class of A. So any element in the conjugacy class of A will generate the same conjugacy class. Now that's of course true whether this conjugacy class just contains one element or whether it contains more elements. Okay, so the overall theorem that I have from this is that if you have a conjugacy class, any element in that conjugacy class will generate the same conjugacy class. Okay, whether it's only got one element in or more elements in it. Okay, right. The next thing then that I want to say is that either the conjugacy class of A covers the entire group, okay, so either it is the entire group or there is another element that is in the group capital G but is outside of the conjugacy class of A. Okay, now if the conjugacy class of A covers the entire group, then you do in fact already have a partition. Okay, it's not a very interesting partition, it's a partition containing one subset, which isn't even a proper subset, but it is still a partition. Okay, if it's not the case that the conjugacy class of A covers the entire group capital G, then you're going to get a more interesting partition. Okay, and there will be some element of the group which we'll call little b, which will be outside of the conjugacy class of the element little a. Okay, then what you can do is you can generate little b's conjugacy class, which we'll call the conjugacy class of little b. Okay, and I'll colour the conjugacy class of little b here in vivid purple. So there's the conjugacy class of little b. And my next theorem, I feel like saying my next trick, is to show that the conjugacy class of A and the conjugacy class of B are completely disjoint. So what I now want to show is that the conjugacy class of A intersects the conjugacy class of B is equal to the empty set if little b was not an element of the conjugacy class of little a. So I assumed little b was outside of the conjugacy class of little a, okay? And what I claim now is going to be true is that, in fact, the entire conjugacy class of little a is completely disjoint from the conjugacy class of little b. So there is no element that these two conjugacy classes have in common, okay? Their intersection is the empty set. Okay, so how am I going to prove that? Well, I'm going to do it by a proof by contradiction. So I'm going to assume the exact opposite. I'm going to say, okay, let's say that there is an element that's in both of these conjugacy classes, and I'm then going to use that to disprove this assumption that B was not in the conjugacy class of A. So I'm going to use it to prove that B was in fact in the conjugacy class of A, which of course is a blatant contradiction because I assumed B was not in the conjugacy class of A. It was outside of the conjugacy class of A. Okay, so I'm now going to assume the exact opposite is true then. So I'm going to say some element in the conjugacy class of A is equal to some element in the conjugacy class of B. So some element in the conjugacy class of A looks like this, GA, G inverse, where little g here is some element of the group capital G, and some element of the conjugacy class of B looks like this, G bar A, G bar inverse, where again, that should be G bar B, okay, where G bar is some element of the group. So quite simply, what I'm saying here is this is some element of the conjugacy class of A. Okay, so you let G be some element of the group, that's all we know about it. You conjugated little a by that element little g, that's some element of the conjugacy class of little a. Here we've got some element of the conjugacy class of little b, we've got some other element of the group which I've called little g bar, we've conjugated little b by this little g bar, we've got some element of the conjugacy class of b. I'm now saying that if this isn't true, then this is true. There's some element that's the same in both of these conjugacy classes. So what I'm now going to use this to do is prove that in fact b is in the conjugacy class of a, which is a blatant contradiction of this basically. Okay, so how am I going to do this? Well, I'm going to take these two things from being on this side to being on this side. So how am I going to do this? Well, I'm going to firstly try and move this onto this side, and the way I'll do that is by composing both sides of the equation on the left with g bar inverse. So let me go through this nice and slowly. Okay, so I've now taken this and composed on the left with g bar inverse, and when I compose on the left here with g bar inverse, I'll get the identity element back again, so I can just write this as b g bar inverse here. So I hope you agree that I'm allowed to do that, okay? If this was true, this is also true, so these two equations are saying the exact same thing. Okay, now what I'm going to do is take g bar inverse here onto the other side as well. So the way I'm going to do that is I'm going to compose both sides of the equation now on the right this time with g bar. Okay, so what I'll then get is g bar inverse g a g inverse, and then I'll get g bar here, and then when I compose with g bar here, those two things will combine together to give the identity, so this will just become b. So now what I have done is I've written b as equal to this monstrosity here, these five things composed together in the group capital G. But that is not as bad as it looks, okay, and the reason it's not as bad as it looks is that actually we can write this cleverly with a few brackets, okay, so we've got this element g bar inverse g, okay, we've then got the element little a in the middle, and then what have we got over here? Well, I claim we have g bar inverse, whoops, what am I doing here? Oh no, that's fine. G bar inverse G, and then we'll have its inverse, and I claim that I can rewrite this thing here as this. Okay, so bits of this are very easy to understand. All I've done is associate G bar inverse and G here by putting a bracket around them. That's perfectly fine. I've kept the little a right in the middle, that's perfectly fine. This is the most difficult bit, but it's still not that difficult. Okay, so I now claim that this thing that I have here is equal to this thing that I have here. Okay, and something's gone wrong there. Oh no, something hasn't gone wrong there, it's fine. Okay, so this thing here, g bar inverse composed with g, its inverse. How do we do this? Okay, well, we know how we take the inverse of two things composed together. We take each of these things that we've got composed here, we take their inverses and then we compose them in the opposite order. So the answer to what this is equal to is just, you take little g here, you take its inverse, you put that at the front, then you take g bar inverse, you take its inverse, which of course is just g bar, and you put that at the back. So you swap the order and take the inverses. And of course that's exactly what we've got over there. Okay, so this thing here is in fact equal to that thing there. And why is that very, very nice? Because now I can see that this is in fact little a conjugated by this element g bar inverse g. Okay, and that now means that little b has to be in the conjugacy class of little a. Why? Because I've written little b as the conjugate of little a by this element g bar inverse g, which is some element of the group capital G, and that's the very definition of being in the conjugacy class of an element little a. Okay, so now what I have shown you then is that if we assume that there is an element that's in both the conjugacy class of A and the conjugacy class of B, i.e. that the intersection of these two is not the empty set, then I can prove that little b was in fact in the conjugacy class of little a. So if little b truly was outside of the conjugacy class of a, then it cannot possibly be the case that there was some element that was in both the conjugacy class of little a and the conjugacy class of little b. Okay, and therefore truly the intersection of these two must equal the empty set. Okay, right, so these two are totally disjoint sets. And then what you can continue on doing is you can then say, okay, either the conjugacy class of A and the conjugacy class of B completely cover the group capital G, or there's some other element, little c here, that is outside of both of them. Then what we can do is we can generate the conjugacy class dedicated to this element little c here, okay? And this now is going to be completely disjoint from both the conjugacy class of little a and the conjugacy class of little b for the same reason, okay? Because if the conjugacy class dedicated to little c here was not completely disjoint from the conjugacy class of little a, again you could use the same argument here to show that that meant that little c had to be in the conjugacy class of little a. The same thing then holds true relating to the conjugacy class of little c and the conjugacy class of little b. So if little c is not in either the conjugacy class of a or the conjugacy class of b, then it means that the conjugacy class of c has to be completely disjoint from the conjugacy class of a and the conjugacy class of little b. And you can continue this process on until these subsets that you've generated, these conjugacy classes that you've generated, are completely covering the entire group. Okay, and that will therefore form a partition of the group. We'll have this bunch of disjoint subsets which together cover the entire group, and that's what is meant by a partition. Okay, right. Now, the important thing here is that this partition is well defined. And what do I mean by well defined? I mean that if I got two different people to do this, so I gave both of them the same group, and I said, go forth and split this group into its conjugacy classes, they would come back with the same answer provided they knew what they were doing. Okay? And the reason for that is that it truly does not matter what little a, little b, little c you used. It does not matter what representatives of the conjugacy classes you use. Okay? Because what I showed you initially is that any element in a conjugacy class would generate the exact same conjugacy class. So you could pick any representative of this orange conjugacy class and it would generate that orange conjugacy class. You could pick any element of this purple conjugacy class and it would generate that purple conjugacy class. And again with the green conjugacy class and with all of the conjugacy classes in this group capital G. Okay? And that is why it means that different people working out the conjugacy classes using different representatives of the conjugacy classes would get the same answer. And that's what I mean by it being well defined. Okay, right, so what we've seen then in this video is that we can use the conjugacy classes of the elements in a group to partition up the group into this partition basically involving the conjugacy classes. Okay, what we're going to do in the next video is we're going to use this conjugacy class partition to arrive at the class equation.